Hi everyone. In this video I'm going to go over some of the basic principles of calculus, derivatives, and integrals. The good thing is if you've never seen calculus before, it's not anything to be intimidated by, and it's an incredibly useful tool in physics, so we are going to spend the next 6 weeks practicing it a lot. So to begin to understand what a derivative is, I'd like you to think about driving a car. At the start of your trip, your odometer reads 0 miles, and then an hour later, your odometer reads 60 miles. So you know that you've traveled 60 miles in 1 hour. Now, if I ask you, how fast were you traveling? You might answer with the average speed, and you could say, well, I traveled 60 miles in 1 hour, so my average speed was 60 miles per hour. And that's true, that was your average speed, but that's not always very useful. And it also didn't really answer my question. You could have been traveling much faster than 60 miles per hour at some points on your journey. You could have been at rest at some points, and you'd still average out to 60. So that average speed isn't always super useful. So a better question I might ask would be something like, what was your speed at this specific moment in time? And to answer that question, we need one of the most important ideas in mathematics, which is the derivative. To go the other direction, to get the distance traveled from your speed, well, then we would use the inverse operation to that, which is integration. So let's start with derivatives. What is a derivative? So to understand what a derivative is, I want to start by looking at the position time graph of an object's motion. So you can see here on this graph that I'm showing you, you have a piecewise function, right? There are different parts of this function that are distinguishable by the fact that, here, for instance, is a straight line, this is a linear relationship, and then here it's something different, and it kind of abruptly changes right here as well. Now, if I ask you to find the slope of this line right here that I've circled in yellow, you would be like, oh, Miss Fitz, that's easy peasy. This is going to be rise over run, or the change in position over the change in time in this case. And, you might realize that, well, change in position over change in time gives you speed, right? That finding the slope here would give me the speed of this object in that duration of time. And, that's helpful in this case, but the reality is that objects don't always move at a constant speed. Oftentimes, their motion might be graphed something like this, right? Where the speed is changing, and I can tell the speed is changing because the slope is changing here. So this is where calculus comes in. Imagine if you're trying to find the speed of this object at this very instant in time up here along this curve. To do that, you would want to zoom in closer and closer to this curve, right? And you can see that in this red box here, I've circled it to get even closer, right? And I keep zooming in closer and closer, and I see that this tiny piece of this curve starts to look more and more like a straight line. In this case, right, get even closer here, and in this case, the straight line slope tells us something important, right? The object's instantaneous velocity, so the velocity at this very moment. And the closer and closer we zoom in, the smaller we make that delta t, that change in time, the more we can get a precise answer for the speed at that very instant. And this is what calculus does. This is what taking a derivative is. It's finding the instantaneous rate of change, or the instantaneous slope. So the derivative is simply a tool that takes a function and tells us how quickly it's changing at each moment. And now that we know what a derivative is, we should also look at how we represent a derivative mathematically. So first is this notation. If we have a function f of x, then the derivative is written as f prime of x. This is like saying f prime of x is the slope of the function f of x at any point x. Another way of representing the derivative is using a notation like this. You would say dx of dt. And this form comes from thinking about how small a change in t causes a small change in x. All of these notations mean the same thing. We are measuring how quickly a function is changing at a specific point. Now, to actually find a derivative, we don't usually go back to the definition every time. That would be really slow and messy and inconvenient, but instead we use a set of rules that make it much quicker. So the basic rules of finding a derivative are listed here on the right. And although it might look intimidating at first, they're not very complicated at all. And you're also going to be studying calculus either in this MITES program or at your own regular schools. And for these reasons, I'm not going to go through and thoroughly explain most of these rules, but I am going to touch on the ones that are relevant to this class, which would be the first 5. So first is the constant rule right here. Think about the function f of x equals 2, for example. No matter what the input x is, you're still going to get an output of 2. In other words, this is going to be graphed as a straight line, a straight horizontal line, so a straight line with a slope of 0, because it doesn't change. This is an easy one then to find the derivative of, right? It would be 0, right? It's nice and intuitive because the slope is 0. At any time you have a fixed value that doesn't depend on time or position, the derivative disappears. Our next rule is the constant multiple rule. This one is also pretty straightforward. It tells us that if you have a constant multiplying a function, you can just carry the constant through when you take the derivative. The key idea here is that constants don't affect how something changes. They just scale the result. Next is the power rule, and this is probably the most commonly used rule that you're going to see in this class. The idea is very simple. If you have x raised to a power, right, x to the power of n, for instance, you bring the power down, put it in front of the x, and then reduce the exponent by 1. So for a function like f of x equals 3x to the power of 4, you would bring down this exponent 4, multiply it by 3, and then this new exponent would become 4 minus 1, or 3. So you would have the derivative with respect to x of 3x to the power of 4 is equal to 12x to the power of 3. Now, next is the sum and the difference rule, and these are pretty straightforward. If you have two functions being added to each other, to find the derivative, you would find the derivative of the first function and then add that to the derivative of the second function. And same with if you're taking the difference. So for example, if you have f of x equals 3x squared plus x to the power of 3, the derivative of 3x squared plus x to the power of 3 would be equal to the derivative with respect to x of 3x squared plus the derivative with respect to x of x to the power of 3, which would be, well, first I'll take this derivative, so 2 times 3 is 6, then I get that exponent up here is 2 minus 1, or 1, and then plus, and I bring that coefficient, or I bring that 3 down to make it a coefficient of this x, and then that exponent becomes 2. So the derivative of 3x squared plus x to the power of 3 would be 6x plus 3x squared. Now, I'm not going to go into detail about the product rule, the quotient rule, and the chain rule just yet, not because they're unimportant or that you don't use them in physics, because you most certainly do, but rather because we're not going to need them for kinematics or forces or for our first couple of units. And so I'd like to practice our calculus with the basics before jumping into the chain rule, for example. But I do want to shift gears and talk about integration, which is basically the other half of calculus. It's like the inverse operation to taking a derivative. So if derivatives tell us how something changes, integrals are about adding up all of those small changes to recover the entire thing. In physics, you can think of integration as a way to go from a rate back to the total quantity. So for instance, going from speed back to the total distance traveled, right? Which is the inverse of what we had done before, which was take that distance traveled as a function of the time and get to the speed. So here we have the notation for integration. This is called an integral, and the way that I would read this is the integral of f of x with respect to x. And just like with derivatives, constants behave really nicely here. The integral of a constant c is just that constant times x, and then I would add a constant here that I've represented as a big C. So you'll notice that this is the inverse operation, right? Like I mentioned, if I were to take the derivative of this function here, right? If I were to take the derivative of this constant C would go to 0. And then I would take this x to the power of 1. I'd subtract 1 from it. So it goes x to the power of 0, which is 1. So that would go away. And I'd multiply that 1 to c. So I'd end up with just little c. So you can see here how integration does the inverse of what derivatives do. And I just want to point out that this big C here, this what's called the constant of integration, is really important. It reminds us that there are many possible original functions that could have produced the same derivative. So we can't forget that constant C when we integrate. Now, just like derivatives, integration distributes across addition and subtraction in the same way. Now here's our power rule for integration. And again, you know, hopefully after I explain this, you can see that this is the inverse operation to taking the derivative. But if I am integrating x to the power of n with respect to x, what I would do is I would add 1 onto the exponent. So this exponent of x becomes n plus 1. And then I would divide by n plus 1. And of course, I would add my constant of integration c here. So for example, the integral of 2x to the power of 5 with respect to x is equal to, I add 1 to this exponent, and then I divide everything by that sum. So I have 2 times x to the power of 5 plus 1 becomes x to the 6th, and then I would divide this whole thing by 6. So I would get 2 over 6 is 1 over 3. And that x now has an exponent of 6, and I would add my constant of integration here. Thank you guys for watching. I hope that this video explains some things that you've been curious about. We're going to do plenty of practice with this stuff. We'll go back to basic definition of a derivative in our first unit on kinematics. And also I will provide you guys with a practice worksheet for calc and probably some of the other basic math tools that we'll need. So I'll post that on our class website along with the solution key. So that's an optional practice for you guys. So thank you so much. I'll see you soon.